In this video, we're going to be going over heaps, and in particular, we're going to go over a MinHeap. We talked about in the last video how a MinHeap is a really nice data structure for implementing a priority queue. And some of the features of a MinHeap include that it is a binary tree where the minimum value is always at the root node. Because of that, you have access to the minimum element in O1 time. Removal of that element is O log n, but access to it is O1. More so than the efficiency of being able to access the element, the data structure itself is much more natural fit for the priority queue, and you're going to see that as we talk about it. A couple of things about the MinHeap that makes it more natural for a priority queue include that it does allow duplicates, and as you know from a binary search tree, you can't have duplicates in it, so you'd have to handle it some other way. A MinHeap allows you to have duplicate elements in it, so that is a much more natural data structure because priority queues are an abstraction that should allow duplicates. And then otherwise, priority queues always just need access to the min element, and so a binary search tree, you would always have to walk all the way left in order to find the minimum element in it. A priority queue is just more natural because it's at the root, so it's right there. Other features of a MinHeap that are important, the first one is that it's not a binary search tree, so you don't have that natural relationship, oh my gosh, that scared me, between the left and right children of a node. So in a binary search tree, you know that the children left of the node are less and the children right of the node are greater, or the whole subtree left and the whole subtree right. That's not the case here. So searching a MinHeap doesn't really work. There's no efficient way to search it. You would just have to traverse it because there's no order to it. The parents are always less than or equal to the descendants. The equal is the important part because that's what allows you to have duplicates. And then the last thing is that a MinHeap is full. So we know that the last element enqueued into this particular priority queue, if we were using this MinHeap, would be 19 because the elements are just added in order of filling the tree. So all rows will always be full except for the last one, which will be on its way to getting full, but it's always balanced. And so there's no messing with the data structure in order to make sure that it remains balanced either, which is really nice. So the best way to understand the MinHeap is to just talk about how to do one of its functionalities. So we're going to just go through how to pop off the heap, and after popping off, it will make sense how you might insert into it or do anything else you need to do with it. So first, we know what item we need, right? When we are going to pop, we need the root. So we're going to save that value and get ready to return it. But now we need to remove it before we leave the function. So the first thing that we do in order to pop one off is we are actually going to take the last node that was inserted, which is 19, and move it to the root node, or copy it to the root node, and then delete the 19. So we are now left with a MinHeap that is not valid, right? Because one of the criteria of a MinHeap is that the parent node has to be less than its two children. So now we need to restructure it so that that's true. So we do that by doing something called sifting down or bubbling down. They're both used from the root. And all we do is we swap the smaller of the two children with the node that we're sifting down. So in the case of the first sift, we are going to just switch 2 and 19. So 2 is going to move up here and 19 is going to move down here because 2 is less than its other child, 3. Now we're going to repeat again and swap 19 with the smaller of its two children, so that's 7. So 19 is going to go here, 7 is going to go here. And once we reach a leaf node, we know we can stop, and we now have another valid MinHeap. So as you know, that operation we just did is log n in the worst case, and in most cases. So that, not really in most cases, I shouldn't have said that, it's just worst case log n. And that is the algorithm. Oops. More details. Here is a written version of that algorithm that we just did. So you replace the root with the last element. Also, obviously, you have to decrease the heap by 1. If the root has no children, you're done. If there's one child, then just label the child C. If there's two children, then label the smaller child with C. And then if the root is greater than C, then you just swap and continue on repeating that until you've either reached a leaf node or you have satisfied the condition of 6. So that is the algorithm, and that's how it works. So the last thing I wanted to talk about, and you can kind of see generally how the data structure works for a party queue. It's really nice. Now I want to talk about how you can implement the MinHeap tree that we've been drawing as an array. The main advantage of this is that it saves on space because you don't have pointers. You only have to keep track of the data itself. When you have linked structures, you are carrying around pointers for every piece of data that you have, which is slightly more expensive memory-wise than an array, which doesn't have to store any pointers, right? Because all you need to know is where the front of the array is, and then everything's sequential, so you can kind of find where you need to go. So how does the tree get converted into an array? Well, let's first just draw out what we can see and go from there. So we can see that the root node is stored on the 0th element of the array. We can see that when we go to the next node that was inserted, which we know goes from left to right, filling each row, that's in the first element of the array. We can see that the 2 is in the second element of the array. Gosh, I hope you can't hear my dog. It's really loud. The 17 is in the next one, and then you have 25 in the next one, and I think you get the idea. So this is the way that the tree translates to an array. The size is also being kept track of, and the capacity of the array, which is just handled the same way that a vector abstraction would handle it. So this probably looks like it makes sense, but you might be wondering, well, how do we navigate a tree when it's stored in an array, right? Because we know how to navigate a tree because we have pointers that point to the connections, but when you put it into an array, how do you know if you're at the second node? How do you know? I'm going to do another color. I don't think I have another color though. I'm just going to use the red because it's something I'm not using in the spot. So let's say I'm at 2, right? I know that 2 should connect to 36 and 2 should connect to 7. But how do we know that the second element connects to the 5th and the 6th element, right? That's the pattern that we still need to sort out. So if we don't have pointers, how do we navigate the tree? Suppose we are visiting node at index I. Where's I's left child? So pause the video for a minute and see if you can convince yourself what the pattern is for finding the left child of any index I. So the answer is it's 2I plus 1. So if you need to get to any node's left child, you just take that index of that node, times it by 2, and plus 1. So for example, for 2 that we were talking about before, its left node is value is 36, so its location is at 2. So if we did 2 times 2 plus 1, we would get 5. And so that's how you can see that 2's left node is 36. And you could try it out for yourself to convince yourself that it works for all of them. So we could do 17, for example. 17 is at 3, so we would do 3 times 2 plus 1. I should write that in the same order. 2 times 3 plus 1, which would be 7. And so this would be the left child of 17, which is correct. In general, when you need to navigate through a MinHeap that's implemented with an array, the left child is located at 2I plus 1 and the right child is located at 2I plus 2. If you need to go back to a parent, you're just going to do I minus 1 divided by 2 integer division. And that is how you can implement a tree, a binary tree, using an array. When I first learned about this, I thought it was incredible. Like I couldn't believe that it was this simple because you see trees and then you have all these nodes and they're connected in all these bizarre ways and you think it's the only way that you could possibly store it. And then when I saw this, I'm like, why aren't we always doing this? Well, trees aren't always structured. They're not always binary. And so this would only work if they're binary. And then also this would only work if your tree is full, right? So you'd have to have a full tree, otherwise you'd be wasting a lot of space and memory with your array of unused nodes. So the last thing I wanted to talk about with MinHeaps is pop deletes the first element by copying the last element to location I, deleting the last element, and then doing the sift down. So how do we delete the last element in our array implementation? So we don't have a tree, we have an array. Can't deallocate a single element in an array. So how do we delete the last element? Well, in an array, you keep the capacity where it is, but you just reduce the size. And because 19 is the one at the end of the array, the one that you're removing, putting up here, and sifting down, all you need to do is change your size. So when you change your size, you're basically just saying, actually my array ends here. So you leave the data there. You don't need to destruct it. You just need to change where the end of the array is. And then eventually it'll get overwritten as you're doing insertion later. Okay, so that's all for MinHeaps. MinHeap. Thanks.